What's up, guys? Welcome to this series on stochastic processes. In this series, we'll take a look at various model classes, modeling techniques, and statistics that are useful for the analysis of time series data. So for what follows, I will assume that you will have completed courses in or have self-studied topics in linear algebra, calculus, and some introductory probability theory. If you haven't or would like to get back up to scratch, what I'll do is I'll link to some textbooks and relevant resources below. Throughout this series, we'll cover various classes of stochastic processes, and I'll give references to relevant textbooks and materials as we cover them, particular to those model classes. But for today, I'll just introduce you to the concept of a stochastic process, and then we'll start covering particular model classes as we go in turn. So let's jump in. Right, so as usual in the world of statistics, we use mathematical abstractions in order to model the real-world processes. As it happens, for most processes we observe in nature, we do not record only the events related to the phenomena that we observe, but also the times at which they occur, resulting in a particular data type that we like to refer to as time series, i.e., a time-indexed set of observations. Now, in order to model such phenomenon, we thus require appropriate models for such data, and this is the domain of so-called stochastic processes. Now, you might find in the literature and in general discourse on the topic that people may use the term stochastic processes interchangeably when referring to either the process generating the observations, i.e. the phenomena being modeled, and or the mathematical objects being used to model such observations. I like to distinguish between these as the data generating process, taken to mean the physical or notional process which gives rise to the data when being observed, and I reserve the word stochastic processes to encompass the mathematical abstractions we use to model such time series. It's a matter of preference, but I like to make the distinction since it helps later on to distinguish between empirical phenomenon and that which relates to the models being used when one writes up a statistical report. Indeed, it's quite easy to get too confused and misinterpret a model for reality. Nowhere is this more true than in the world of finance. Okay, so now there are numerous canonical examples of time series. The simplest often relate to physical phenomena, such as weather, where we might measure or collect observations on things such as temperature, humidity, wind direction, and precipitation at regular intervals. More complex examples might relate to financial ecosystems, where prices of financial instruments are recorded at varying resolutions, often sometimes at extremely high frequencies, which obviously necessitates special statistical tools for purposes of conducting meaningful analyses. Right, so now that we're clear on what I mean by stochastic process, I can move on to clarify my vague statement about mathematical abstraction. So in order to model time series data, we need to develop appropriate probability models for such observations. So i.e. we need probability models which capture the temporal, as in relating to time, nature of the data. So we start by defining a stochastic process simply as a time-indexed set of random variables. Now recall that in basic probability theory, we typically define a random variable, say capital X, which has an associated random or distribution. We then model observations as realizations being generated from this distribution. Our choice of distribution and parameterization depends, of course, on the context. So, for example, in simple linear regression, we model responses as coming from, say, a normal distribution, and then we parameterize the mean of that distribution as simply being a linear function in some set of explanatory variables. Now, note that though we index the predictors and responses here, there is no explicit notion of direction or time in the index. It is simply there to associate a particular response with a particular set of explanatory variables or covariate pattern. So we collect n observations, and each of those little i's associated a particular response with the explanatory variables. Now, in the case of stochastic process, however, we explicitly index the random variables with respect to time. We thus denote a stochastic process as a set of random variables, say x sub t, where t assumes values in some index set, say cal I, and obviously this index set could represent clock time, regularly spaced points in time, or simply represent the order in which the random variables occur. We also define the state space as the set of all possible values or states that the stochastic process may assume along time. And this will denote cal U. Thus, for a stochastic process, our probability model requires not only picking an appropriate distribution for the state of the process, but also the mathematical description of how the observations are statistically related in time. Now, depending on the nature of the state space and index set, we can distinguish between various joint configurations of stochastic processes. Okay, so we have discrete time, discrete state processes, discrete time, continuous state processes, continuous time, discrete state processes, and then finally continuous time, continuous state processes. Okay, so in what follows, in each of the model classes that we'll cover, we'll teach you how to construct appropriate mathematical models which attempt to capture both the temporal as well as spatial dynamics of processes under each of these configurations. Indeed, as it happens, the order in which I've listed these combinations are likely the order in which you'll learn about their corresponding probability models. This is perhaps a consequence of the mathematics arguably getting increasingly difficult as you go down that list. But in any case, in order to become a well-rounded statistician, one really needs to master all of these. But you need not worry. These are actually all very interesting model classes of processes, and they're very fun mathematical objects to actually learn with. Right, so let's round off some examples of stochastic processes under each of the configurations I've mentioned before. Now, typically a stochastic process is formulated directly as a probability model, indicating how random variables are related in time, or indirectly as a model equation or set of model equations containing the state variables and an explicit temporal relationship. So, an example of a discrete time, discrete state process would be a Markov chain, for which the dynamics are typically defined in terms of a so-called transition probability matrix, which basically dictates the likelihood of particular outcomes of the process over a given transition horizon, depending on the present state of the process. Or in the simplest possible terms, it's just a set of discrete distributions over the state space, each associated with a particular state of the process at a given point in time. An example of a discrete time continuous state process would be a so-called AR1 process, which is short for autoregressive of order 1. Which is defined as a simple recursive relation indicating how successive random variables are related in time, where the stochastic component of that iterative relationship is typically captured by a familiar normal distribution. An example of a continuous time discrete state process would be a continuous time Markov chain, where the dynamics are determined by a so-called generator matrix and a set of differential equations, which governs how the transition probability matrix evolves continuously over time. So essentially a continuous time counterpart to what I was mentioned before. Finally, an example of a continuous time, continuous state process would be an Unstein-Uhlenbeck process, which arises as a particular specification of a so-called stochastic differential equation or diffusion process. Now, as it happens, this is my domain of research, so hopefully in future I'll be able to tell you more about that. Now, regardless of how these processes are defined, a unifying concept which applies across all of these configurations is that of the transitional distribution. Again, recall that in basic probability theory, we define probability models in terms of appropriate distributions. In the present context, where there exists an explicit temporal relationship between the variables, the transitional distribution captures how the collection of random variables, which defines the process, are related in time statistically, depending on the state it assumes at any particular point in time. This distribution may define the process as in the case of a Markov chain, or it may be implied by the model equations, such as in the case of the AR process or diffusion process. So to give you a feel of what these objects represent, we can plot the transition distributions for the examples I've mentioned earlier. So in the case of a Markov chain, the distribution resembles a mass function, evolving systematically over discrete time steps. This gives us the probability of the process assuming one in a discrete set of states at discrete points in time, conditional on starting in a particular state at the outset. In the case of an AR process, the transitional distribution looks like a sequence of normal distributions, giving the distribution of the values of the process at discrete points in time, conditional on a known position at the outset. In the case of a continuous time Markov chain, the behavior is similar to the discrete case, only with the distribution evolving continuously over time. So similarly, the Ullstein-Uhlenbeck process, its transitional density mimics the behavior of the AR process, but only continuously in time. Now, we'll get to the details of these objects later, but the important thing to take away from this is as follows. In defining a stochastic process, we create a time index set of random variables. As in the case of basic probability models, we still employ the appropriate distributional assumptions, whether explicitly or implicitly via the model equations, so as in the AR process or Ullstein-Uhlenbeck process. But the principal difference is the addition of the time dimension, and where the models are concerned, how random variables are statistically related in time, which makes them appropriate for modeling observations which exhibit empirically some statistical relation in time, so i.e. time series observations. Right, so that concludes it for our introduction to stochastic processes. I hope you found that interesting. This will probably be the jump-off point for a model class under any of the configurations that I've mentioned before. But in any case, I'll see you in the next one. Cheers.